Okay, welcome back. We are still talking about equilibrium. We will be doing that for a long time. In this video, we're going to start introducing some math to describe the equilibrium of a reaction. So imagine that you have some chemical reaction like this. Very simple, A turns into B, and you reach equilibrium. In other words, the concentration of B, whatever it is, stops changing. The concentration of A, whatever it is, stops changing. Maybe it's 75% B, 25% A, something like that. We want a way of describing what the equilibrium situation is for our chemical reaction, and we want a way of describing it with a number so that we can compare it to other chemical reactions under different conditions. And there is a way that it's done. This is the standard way, and there are a number of good reasons for this, but we're not really going to go into the good reasons for it. The way that people describe the equilibrium of a chemical reaction is to use something called an equilibrium constant. And the equilibrium constant is usually abbreviated with a capital letter K and sometimes with a subscript of EQ, which stands for equilibrium. Sometimes the equilibrium constant is abbreviated with a capital K and a subscript of C. That means concentration. And other times the equilibrium constant is abbreviated with a capital letter K and a subscript of P, and that's usually used, the P stands for pressure. That's usually used when all of the things in your chemical reaction are a gas, and you can measure the pressure that they exert, which is going to be related to their concentration. So equilibrium constant can be written in a bunch of different ways. Probably the most common way that I will write it is KEQ, but you'll see it as KC and sometimes KP as well. Now I haven't described what the equilibrium constant is or how you calculate it, but we're going to do that right now. So imagine that you have some chemical reaction, and this is a little bit more complicated than what I've shown you before. These little a's, these little letters, the little a, little b, little e, and little d, those are the numbers that would balance this pretend chemical reaction. And the capital letters, the A, B, E, and D, those are the actual reactants and products in the chemical reaction. Just to give you a more concrete example, here is a balanced chemical reaction. There's a 1 here. If this were the equivalent of this reaction over here, this 2 is basically the little a. This 1 is the little b, and the H2 here is the A, and the O2 is the B, and this 2 here might be the little e there, and the H2O would be the capital E there. In this balanced equation over here, we don't have 2 products. We only have 1. We only have water, so there is no D in my more concrete example of a chemical reaction over here. But we're going to keep it very general, so this is just a general chemical reaction. And if you wanted to describe the equilibrium constant, the KEQ for this chemical reaction, here it is. The equilibrium constant is going to be equal to the concentration of E, whatever the E molecule is, raised to the little e power, times the concentration of D, whatever the D is, the capital D, raised to the little d power. And then that's all divided by the concentration of big A, whatever A is, raised to the little a power, times the concentration of B, again, whatever that is, raised to the little b power. And this is the situation if you have 2 products. So there's my 2 products, and 2 reactants, there's my 2 reactants. But you could have 50 reactants and 50 products. You would just do the same thing. You would multiply all of the products together, raised to whatever power you're supposed to raise them to, and divide them by all of the reactants multiplied together. Well, the concentrations of the products and the concentrations of the reactants. If you remember, that's what those square brackets mean. Those square brackets mean concentration. And these concentrations, right, these things in square brackets, even in the generic equation over here, the numbers that you use to go in those concentrations are when the concentrations stop changing. This is KEQ is only when these concentrations have stopped changing in your chemical reaction. So there's a couple of things that we can say when we calculate KEQ. First thing is, if our equilibrium constant, if we do this calculation and we end up with a number that's bigger than 1, that means the numbers in the numerator, when we multiply them together, are bigger than the numbers in the denominator when we multiply those together. But the numbers in the denominator come from the left side of the arrow, and the numbers in the numerator come from the right side of the arrow. So if our equilibrium constant is bigger than 1, it means the things on the right side of the arrow are basically, I don't know, this is a little bit not correct, but I'm going to say it this way. The amounts of the products are winning compared to the amounts of the reactants. So if the equilibrium constant is bigger than 1, what you usually say in chemistry is the reaction favors the products, because it means the numerator or the right side of the arrow in this reaction is winning compared to the left side of the arrow. And if the equilibrium constant, if you do this calculation, and the equilibrium constant turns out to be less than 1, that means the denominator is winning, and the denominator represents the left side of the arrow. So if the equilibrium constant is less than 1 for your reaction, then you say the reaction favors the reactants. So this is equilibrium constant bigger than 1, less than 1, is a way of trying to figure out once the reaction hits equilibrium, who's winning, the left side or the right side. Now it's not a perfect way of describing this, but it works reasonably well. And obviously if the equilibrium constant equals 1, then neither side is winning, I guess. There is another term that's related to equilibrium constant, and it's abbreviated with a capital letter Q, and it stands for reaction quotient. The reaction quotient, the formula for calculating the reaction quotient, is the same as the formula for calculating the KEQ. But there's one little difference. The reaction quotient can be calculated at any particular time when a chemical reaction is taking place. It doesn't have to be calculated at equilibrium. So Q is just the same kind of calculation, but at any point in the chemical reaction. Another way of thinking about this is the equilibrium constant is just a special version of Q, but it's the special version when the concentrations stop changing. So I don't know, if it helps, maybe repeat that a whole bunch of times in your head. KEQ, or equilibrium constant, is just a special situation of the reaction quotient, and it's the situation when the reaction has reached equilibrium and the concentrations of the reactants and products have stopped changing. Now you should basically know how to calculate an equilibrium constant if you see a chemical reaction that's properly balanced. Here is an example of a balanced chemical reaction. It says, how would you calculate Q for the reaction below? Or we could just say, how would you calculate the equilibrium constant for the reaction below? You can pause the video and try to work through this. It's very similar to what we did on the previous slide. All right, if we unpause, the equilibrium constant for this reaction would be the concentration of NH3 raised to the second power. NH3 is our only product, so it's going to go in the numerator. The 2 is going to go there as the exponent, divided by the concentration of N2, raised to the first power because there's no coefficient in front of the N2, times the concentration of H2, raised to the third power. That's our other reactant, and there's a 3 in front of that, so we're going to raise that to the third power. And this, if you did this calculation when the concentration of these 3 things was not changing anymore, then you plug them into this formula, then you would calculate equilibrium constant for this reaction under a certain set of conditions. If you were not at equilibrium and you did this calculation, in other words, you just took a snapshot of the concentration of NH3 and the concentration of N2 and the concentration of H2 at just some particular time when the concentrations were still changing, but you could take a snapshot of their concentrations and you plug those concentrations into this formula, then you would be calculating Q, or the reaction quotient. All right, that is it for this video.